This is Programming Cube Puzzle 1 through 3. So these were 3 related challenges where they're going to give us a Python pickle file, and each pickle file is going to contain a set of pieces, these puzzle pieces. And our job is to reconstruct the puzzle and read the diagonal elements, and that'll print out the flag. The first one is a 2D puzzle. And like I said, we're just supposed to put the puzzle pieces together based off of the edges, making sure they match, and then read it out. The second challenge was a 3D puzzle. So just an extra dimension, just more edges to match up. And then the last one was, again, a 3D puzzle, but it was almost a gigabyte of puzzle pieces, which is a lot. And so you just had to make sure your time and space complexity were sufficient for handling about a gig of data. But yeah, let's take a look at the diagram first, and then I'll start covering the solutions, just to make sure everyone's on the same page. So like I said, they're going to give us these pieces. This is the format of the piece. So there'll be a couple hundred of these. I think the first challenge starts out with 4,000. So it'll have an ID for up. So this could be like, 500, 300, 100, and 200, random numbers. And it's important to remember these are the IDs of the edge, not the IDs of the each individual piece. And then each piece has its own payload, which is just a character. And so the idea is, like, if you had 2 puzzle pieces matching, the ID for down might be 100, and the ID for up for this one would also be 100, so they match. So every once in a while, every edge does have an ID. And so part of the trick for my solution, there's probably multiple solutions, is if you look at a edge, like at the very edge of a puzzle, there's no connecting thing here. And so this would have no matching ID. So like if it was ID 15, no other edge should have ID 15. And so you kind of know it's an edge piece. They gave us a little image just to kind of show how it works. So we can see right here there's a 1 through 3, 7, and on the left there's a 1 through 3, 7. So these two pieces join together. And we need to construct something like this, and then to read the flag you just read the diagonal. And that was it. So my solution, I kind of hinted at it already, is I focus first. The first thing I want to do is figure out what this top left piece is. And then from there I just iterate down and I read the diagonals. I don't really care about reconstructing the board or anything. To figure out which piece is the top left corner, I go through and I find all the edges that are lonely. And so we know that, like this piece is this ID on the top of A. Here, I guess I can zoom in. This piece up here is going to have an ID of like 3. And since it's alone, there should be no other piece that has an ID of 3. So what I first do is I find all the lonely edges, the edges that don't match. And then I go through all the pieces and I see which one has it such that the top and the left are both lonely pieces. And then I know that one is the top left corner. Once you know which one is the top left corner, I think the challenge is much simpler. At that point, you're just going to go, you know what this piece is, so you're just going to see what is the ID of down. You're going to find that the piece that has the ID equal to that with up, and then you're going to move to the right. So you have this piece, you're going to say, what is my right? Find a piece that matches on the left, and then you have the F, and we're just going to iterate down, 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 and we'll be able to get the flag. So to see what this looks like, we're going to import the pickle library, and we load it here. You just do pickle.load, open the file, nothing too fancy, and you print out the pieces. I think for this one, I think it's 4,000. I defined some constants just to keep things a little clean. Like I said, this code could probably be cleaner. I just wrote it real fast. This is find edges IDs. So I'm going to find all those lonely pieces, and I'm just going to record all of the IDs. And how I do this is for piece in pieces, for ID in pieces. So I'm going to iterate for all the pieces. I'm going to take all 4 directions. If it's not already in my known dictionary, I'm going to create an entry for it. Otherwise, I'm going to increment by 1. Then I go through that dictionary of all the IDs and I see which one only had a count of 1. And if it has a count of 1, you know it's lonely. So we found all the possible edges. At this point, we're going to find the top left corner. And so to do this, I just go through all the pieces. I just use this filter lambda function. And I'm going to go through all the pieces, and I'm going to see if the up and the left for that piece are both in the lonely edges. And if they are, there should only be one of those, and we know that's the top left. Cool. Then I start constructing the flag. So I say flag is equal to the current one, the top left one, and then we're just going to iterate down until it errors out. And you could do some error checking logic, but basically at some point it's not going to return anything and it's going to throw an error. But at that point you've already printed out the flag, and so you've won. So first step is to go down. So like I said, we're going to take our current piece. We're going to match the up with its down. And so we're moving down 1 square, and then we're going to move right 1 square. So we're going to say, take the current right, match it with a left. For all the pieces, and then you have the next flag square, and then we just add that to the current flag we're building, and you print it out, and we just keep looping, and we should be able to solve it. So the first one was called cub, so we'll do python 3 solve. Filter expected, oops, sorry. I copied some code from my solution for the next one was a little bit easier, so I was cleaning up the first one. And there we go. This is the string for the flag. If you just copy this out, put the hero brackets in and submit it, you get the points. For the second one, again, thankfully it wasn't too much harder. We just needed to do it in 3D. So in this case, we defined some more constants. So now we have front and back are two additional variables we need to think about, but it doesn't really make anything too much more difficult. Again, I have it like this. So we're not going to do this top left corner. It used to be, so there's two different ways to do this. I converted everything into filters. Actually, I'll talk about that in a second. Anyways, so we load the puzzle. We do the same sort of find edges. Instead of going from 0 to 4 for up, right, down, left, we have to go 0 to 6 because we also need front and back to see if they're lonely pieces. We're no longer dealing with edges. Now we're dealing with planes, but they're still called edges. Like now it's a cube, and so, you know, on the edge of one of the cubes, you're just going to have a whole plane face. But that plane face still only gets an ID. And so we're going to look to see how many of these IDs are only occur once, then we know it's an edge, and then we're going to find the corner. So for the top left corner, we know that the up, the left, and the front of the piece all have to be a lonely edge. And there's two different ways you could do this. This is, I guess, one Pythonic way to do it. So find top left corner for piece and piece. If the piece matches all those conditions, return piece. I think filters might be a little bit faster. I could be wrong, but for the last challenge, I converted everything into these this filter code, just so it's faster, and I just didn't do it for all this one. So we want front and edges. Cool. And we'll take this. So let's print it out and see if it works. Oh, and the rest of the code is the same. So instead of going, we're going to match up and down, we're going to match left and right, and then we're going to match front and back. So we're just adding an extra dimension. So this is ePoo. Then we do clear Python 3 solve, and it prints it out. I'm pretty sure this was the flag, so just wrap that into HeroCTF and you got it. The last one was the same, except the file was huge, so you had to download it from here and unload the file. And there's also one other thing where you only grab the third flag, or the third character out of all of them. Like it says, if this was the string, then you should only return A1D4, so the third element of the string. But we just had to make one change to make this slightly more efficient so that it would run. And we need code solve. Cool. So we do the same sort of stuff. It's still 3D. We load it in. We find all the edges. So the time complexity of this would still be O of n. So this is kind of CS sort of stuff, but it's going to iterate over each piece, and there's n pieces, and this isn't really doing much. So yeah, it's just going to be O of n adding to a map. I guess it also depends on the map, but we're just going to say, you know, it's amortized one insert. So it should be O of n. Then for this, we're building out, we're going to iterate through all the IDs again. So I guess you could say O of 2n. It's not quite correct because you'll just get rid of the constants out front. So it's just still going to be O of n. So not too bad. From here, the change we had to make is here. So it used to be we would check, we're doing this if x up is in the edges array. So we had an array of all the lonely elements. To search if an element is in an array, you have to scan over that entire array. And so if you have, you know, 1 million elements in that array, it has to do 1 million checks. Instead, a better data structure to use is a map or a dictionary. Checking if a element exists within a dictionary. I'm guessing Python under the hood probably uses hash maps. It should be O of 1, which just means it's constant time. For the most part, I think depending on your hash map implementation, there might be an array and bucket sizes, blah, blah, blah. But for the most part, you can just say kind of like it averages out to O of 1. And so instead of doing, O of n, each one of these lookups is O of 1. And so if we were doing the array, I mean, worst case would be like n squared, which would be too much for this. But since now this is a O of 1 and we're going to iterate through all the pieces, it should be O of n, and it is now possible to figure out what the top left corner is. From there, the rest of the code is the same. Thankfully, it really wasn't too bad. We can iterate over, I think it's like maybe 1 million elements, I forget. We can iterate over 1 million elements without too much trouble. We could probably iterate over, 10 or 20 million. If you think your processor runs at about, 2 gigahertz or so, So, you know, back of the napkin calculation, you can do 2 billion operations. So you could say you could probably, like if your code was highly optimized, do a compare, you know, every 3 or 4 operations. So, you know, you can probably iterate, you know, a couple 100 million or more things. And so that's kind of back of the napkin. So if it's, you know, a couple million, we should be fine. This does consume quite a bit of memory. Like I said, it's about a gig of stuff. Which actually makes me think it was probably more than 1 million items, but it was about a gig. I think I checked the process while it was running. It takes about maybe 5 minutes to run, and at the peak, the process was using about 2.5 gigs of RAM. So you definitely need a computer that can handle that. There might be a faster way. You could probably break this into chunks, but that's just what I did. So this is still going to take a second. Python 3, solve.py, but just to show that it works. And we can see how many elements there are. So I'll speed this up. There were 7 million elements. There we go. Sweet, there we go. So you might have saw it was using 2.5 gigs or 2.6 gigs. If we scroll up a little bit, we can see this is how many pieces there were. This is how many edge pieces there are, so about 250,000. It found the corner piece. This is the IDs of the corner piece that starts with a 2. And then from there, we just, you know, do the down, left, right thing, or front, back thing. And it prints out the flag. So this is the flag. Like I said, the last step was that you had to take out every third element. So pretty easy to do that. You just sign it a variable. So we said A is equal to that. Then you can do A like this, and you'll get out every third element. So wrap this in a hero, and there was the flag. So, fun challenge.